All right, so this is for exam 5 on chapter 7. And we're talking about atomic structure and periodic trends in the table. All right, we'll take the easy ones first. Which forms of electromagnetic radiation has the longest wavelength? Remember the system or the electromagnetic spectrum, we have the visible in the middle. If we go wavelength gets longer this direction, then we'll go the other direction. That's all right. On this side, the longer wavelengths are going to be, this is going to be the red end. This is going to be the violet end. So we're going to have infrared right here. And then comes microwaves, and then radio waves would be the longest wavelengths. If we go the other direction, we're going to have ultraviolet here, right? And then we're going to have X-rays. And then we're going to have gamma rays. I can do better than that. Gamma rays. Okay, so let's see. What about the number 1? I don't know why I skipped number 1. When ignited uranium compound burns with a green flame, this is 1. Burns with a green flame, the wavelength of the light given off by this flame is greater than that of. So if it's green, we'll go the other direction. Red, orange, yellow, green. So it's going to have a wavelength is greater than. So this wavelength is going to be greater than anything on that end. Greater than indigo or violet or anything here. So we have red, infrared, radio, ultraviolet. It's going to have a longer wavelength than ultraviolet out of those that were given. Let's go down to 3. I'll leave that up there in case we need it again. Which of the following frequencies corresponds to light with the longest wavelength? Remember, speed of light equals wavelength times frequency. So that means that the wavelength and frequency are inversely proportional. When this gets bigger, that gets smaller. So if we're looking for light with the longest wavelength, this is the longest wavelength, we want the smallest frequency. So first thing I do is look at the powers of 10. Right? And they're all different. So B has the smallest power of 10, 10 to the 5th. And that reciprocal second, let's see, it's 4.12. 4.12 times 10 to the 5th. Reciprocal second is another unit for hertz or cycles per second. Since cycles is not really a measurement, sometimes we just leave it off and just say s to the minus 1. All right, let's see. I want to get to number 6. A line in the spectrum of atomic mercury has a wavelength of 254 nanometers. So its wavelength is 254 nanometers. When mercury emits a photon of light at this wavelength, the frequency of the light is. Okay. It's just saying a lot of that is gobbledygook. It's just saying, what is that in frequency? Okay, so since this relationship still holds, right, then we want to find out what that one is. And if we solve for that one, then we have speed of light over wavelength. But these have to be in SI units, right? This is meters per second, and this has to be in meters. But that's not meters. So when you have a unit like this, I think the easiest way is to say, what does nano mean? Nano means 10 to the minus ninth meters. So we just multiply that times 254. And that'll go into your calculator just as easy as scientific notation. All right, so let's see. We need 2.9979 times 10 to the 8th meters per second is the speed of light. And then we would put 254 times 10 to the minus ninth meters. And numerator, denominator, that cancels. Denominator, it's going to be reciprocal seconds, which is what we expect from frequency. 2.9979, 8. And then divide by 254 exponent. That's 9. And I get, let's see, 3 significant figures. 1.18 times 10 to the 15 reciprocal seconds. Okay. Right. Let's see. Number 8 coming up. I think we can get rid of this now. Green light can have a wavelength of 543 nanometers. The energy of a photon of this light is. Okay. So we have a wavelength of 543 nanometers. And we're looking for the energy of that photon. So the formula that you need there is in useful information, right? And it's Planck's constant times frequency, but we have wavelength. So what we want to do is derive an equivalent expression for frequency, which would be C over lambda. Okay, so this is going to be Planck's constant times C over lambda. Okay, Planck's constant, 6.6 something 10 to the minus 34. That's why I put it in useful information. So I wouldn't have to memorize it either. 6.626 10 to the minus 34. Let's see. What were the units on that? It would be joule seconds, I think. Okay. And speed of light hasn't changed. Meters per second. And then the wavelength, we need to do that transformation again. 543 times 10 to the minus 9 meters. Right? Yeah, meters. Okay. And if we look at the units of measure, just to be sure, right? Numerator, denominator cancels. Numerator, denominator cancels times joules, and that's our energy, is in joules. So let me see. 626. And So I get that photon has this much energy, 3.66 times 10 to the minus 19th joules. Is that what you get?
More.
Okay. That's just for one photon of light. That one quantum of light associated with this color. So if we had a shorter wavelength would mean what? Shorter wavelength would put a smaller value here. When you make the denominator smaller, the expression gets bigger. So that makes sense. The wavelength gets shorter, the energy gets bigger. All right. Let's look at number 11. How many of the following are correct? Oh, okay. Let's see. That one. There's only 4 of them. Okay. So the first one, the importance of the equation E equals mc squared is that energy has mass. I'll go with that. Yeah, that one's true. The second one, electromagnetic radiation can be thought of as a stream of particles called photons. Yeah. Can be thought of as. Nobody's ever seen them. Electromagnetic radiation exhibits wave properties. Yeah, that's true also. And energy can only occur in discrete units called quanta. They're all true. Every last one of them. Okay, let's see. We've got 1, 2, 3, 4 that are based upon this table. So let's see, we're starting at 12, 13, 14, and 17. So electrons have let's see, what are we supposed to do with it? From the following list of observations, choose the one that most clearly supports the conclusion for the following questions. Okay, electrons have wave properties. What observed phenomena supports wave properties? Emission spectra? No, that's not a wave. Photoelectric effect? That's not a wave either. That's particles. Scattering of alpha particles by metal foil? Nope. Diffraction. There you go. There's the ticket. Diffraction. Remember what diffraction is? It's the bending of light around an object. It can happen around like a wall, and you got a wave coming through. It hits that wall, and then it serves as a point source for the next wave. And it just propagates out like that. Or a slit. You can do the same thing with a slit. That. And this would serve as the point source for the next wave. That's typical of wave properties. And you can see that in water wave tanks, where they have a tank of water, and they have this wave generator that just kind of moves up and down and make the water jiggle, and the wave propagates across the water. If you put something in the way like this, then you can see the wave propagate out just like that. And light behaves that way too. Let's see, 13. Electromagnetic radiation has wave characteristics. Well, the first one was electrons. I use the light as an analogy, but electrons will do that too. Electrons, and we use that effect to image things in electron microscopes. That wave property of electrons is what allows us to see very fine detail because there's a diffraction limit, they call it, for the radiation that's being used. So if you use light, there's a lower limit to how the difference between two objects that you can see. Anything below less than the wavelength of the light, well, there's a formula that goes with it, but it's a diffraction limit. And you can only see things down to a certain size with light microscope. But if we use electrons, electrons have a much lower equivalent wavelength. So we can image things of a smaller size with electrons. Now, if you could get me going fast enough to image something, I'd have a wavelength that is orders of magnitude shorter than the electron, but I wouldn't survive the operation. Okay, so 13, electromagnetic radiation has wave characteristics for the same observed phenomenon, diffraction. Electrons and atoms have quantized energy. All right, so where does that fit into our phenomenon? The emission spectrum of hydrogen is a line spectrum, which tells us that the jump that an electron makes in the hydrogen atom, like if the electron's here and it jumps to here, higher energy to lower energy, it's going to give up light. But it doesn't jump from here to the middle. It only jumps from one energy level to the next. That's quantized energy. And the emission spectrum of hydrogen is a good example of that. Let's see. Well, we didn't get down to cathode rays. What is a cathode ray? Cathode ray is a stream of electrons. That's it. J.J. Thomson figured that one out. And the last one. Spacing between atoms in a crystal is on the same order as the de Broglie wavelength of accelerated electrons. All right, this is also a wave characteristic of electrons. Second semester, we'll look at that in more detail. There's an equation called the Bragg equation that uses this phenomenon to measure the distance between rows of atoms in a crystal. It's a fairly simple technique, really. I used it on the soil samples. I was trying to figure out what type of clay was in the soil sample, and just fire wavelengths, X-rays at it this way, and you scan through various angles, and then you measure the intensity on the other side, and you can tell with this equation what's the spacing between the plates of your clay particles, and that will give you information for what type of clay it is. There are lots of different types of clays, but essentially two types. Ones are static and the others are expanding lattice. So when they get wet, they go. Otherwise, they just sit there. Okay, 16. The 4 lines observed in the visible spectrum of hydrogen tell us that, well, they tell us that the electrons only move between certain energy levels and nothing in between. What would happen if the electrons were allowed to begin and end anywhere they wanted to outside the atom? What kind of spectrum would you observe? if the jumps are infinite in size, the number of wavelengths you get would be infinite also, right? And all you get from the atom would be white light. So every atom with its electrons would just, when it's excited and it relaxes and gives off energy, it would always be white. There would be no way for us to tell anything about the universe out there because everything we receive would be white. But since we do get these quantized jumps, and D is the best answer, these quantized jumps, they're characteristic of every atom. It's like a fingerprint. So you can measure the spectra, the line spectra of atoms giving off energy from distant stars. And you can tell what their composition is, elemental composition. You can also tell, say you have a cool cloud of gas between the star and you can pick up dark lines where light was absorbed at those given wavelengths. And that will tell you what's in the cloud. Okay, that was D. 17. For which of the following transitions does light emitted have the longest wavelength? All right, the longest wavelength is the shortest or the smallest frequency, which would also be the smallest energy. So when we say smallest energy, that means the electron jumps the shortest distance. Right? So if we have a nucleus here, and we have, there's energy level 1, there's 2, 3 gets a little bit closer, 4 gets even closer than that. How many do we have to choose from? Just 4, that's good. Okay, so if it jumps from 4 to 3, right? That's a pretty short jump. If it jumps from 4 to 2, that's more energy. Right? If it jumps from 4 to 1, that's a lot more energy. If it jumps from 3 to 2, kind of intermediate. This one's still the shortest. And 2 to 1 is intermediate. But the shortest jump, given the smallest wavelength, the smallest energy, or the longest wavelength would be A, would be 4 to 3. That's the shortest jump. And you need to recognize that the first energy level, wherever it happens to be, I just picked a place. The second one is out a certain distance, and the spacing between them gets shorter and shorter and shorter as you go out. So 5 would be here, 6 would be there, 7, they'd be so close we couldn't even see them on that scale. Okay, so that was A. 18. Let's see. When a hydrogen electron makes a transition from 3 to 1, that one's not shown. Let's go from 3 to 1, and we have 1 proton here and 1 electron, discounting those others. Which of the following statements is true? Energy is emitted. Yep. We're going from a higher energy to a lower energy, and we have to conserve the energy, so it gives up energy as light. It can't give up and absorb at the same time, so 2's out. And so we get number 1 is true. 3, the electron loses energy. Yep, it sure does. It loses energy and gives it up as light. And 4 is just the opposite, so we can't have that one. 5, the electron cannot make this transition. And that's bogus. So 1 and 3, that's B. Those are valid statements for the or number 18? Let's see, how about 21? Which of the following is incorrect? All right. A, B, C, D, and E. Emission spectrum of hydrogen contains a continuum of colors. Yeah, that's incorrect, right? Do we have any wonky ones in there? No, we found our answer. B through E should be correct. Diffraction produces both constructive and destructive interference. Yep, that's true. All matter displays both particle and wave-like characters, and it's true. That's one of de Broglie's postulates, that anything that moves has a wavelength. So if I'm running down the hall, I've got a wavelength. Actually, if I'm just standing here, I have a wavelength too. Niels Bohr developed a quantum model for the hydrogen atom. Yes, that's true. His was the planetary model, right, which has been debunked, but it was a starting point. The lowest possible energy state of a molecule or atom is called its ground state. Yes. And the ground state for, say, the hydrogen atom is N equals 1 at these temperatures and pressures. If we elevate the temperature, say we take hydrogen to surface of Venus, its ground state's going to be higher because there's more energy in it. The more ambient energy is causing that electron to sit higher at those temperatures. That's a different ground state. But typically when we say ground state, we mean at, 25 degrees Celsius, 1 atmospheric pressure. 22. No, yeah, 22. Which of the following statements best describes the Heisenberg uncertainty principle? All right. What did Heisenberg actually say? Heisenberg was referencing the variability in determining either momentum, right, which is that's the Greek letter rho, which equals mass times velocity. So he was saying any variation, that's what the delta means, any variation in that factor is one to be considered, along with position. And we just use an X for that one. Right, so the variation in position times the variation in momentum, right? Those two has to be less than Planck's constant over 4 pi, I believe, if I'm not mistaken. Let me check to see. See if my memory is holding up. Maybe I didn't put it in here. I don't see it. Or is it 2 pi? Anyway, less than or equal to, which just means that since this is a constant and that's a constant, this is a constant value. So these two multiplied by each other has to be equal to or less than that value. So that means that if the position varies a whole lot, I mean, if you say like an electron, it could be here, or it could be there, it could be there. If we let that one be real big, then this one can be small, right? And if we're talking about electron, then the mass isn't important. We're talking about velocity or energy. So that we can determine the energy very precisely if we let the position just do what it wants. The other way around, if you try to determine its position, then you can't know what its energy is. Not with any degree of precision. That's all he's saying. Okay, that's mathematical. Now in words, right? What we're saying is it's impossible to know both the momentum and the position of a particle, especially if they're very, very small. And that C fits that one pretty close. And Heisenberg came up with this one. He was taking 2 weeks off from. He had to ask permission from his supervisor. 2 weeks off, and he went to the ocean. He thought the sea air would help him. He has severe hay fever allergies. I mean, they were just monstrous. And they didn't have the drugs back then that we do now. So he thought the sea air would help him. While he was there, you can't shut your brain off. So he was thinking about something. He said, he was thinking about the prevailing theories at the time and said, wait a minute, these are just speculations. He says, if I base my theories or my conclusions on reality, then I can get closer to a viable theory. So that led him to this proposition. I don't know how he did it, right? But that's where he ended up. And that was on his 2 weeks vacation. I'm not sure what his professor had to say about it when he got back. Actually, not. It wasn't his professor by that time. He was a research assistant. So he was earning a living and learning at the same time. Okay, 25. Now we're going to look at the electronic structure of atoms. How many f orbitals have the value n equals 3? All right, let's go back and review. Principal quantum number. And then these can be from 1, 2, 3, whole numbers, all the way up to whatever. And then each one of these can be subdivided into magnetic quantum number, I think. Or is it angular? That's magnetic. The next one is angular momentum. This one can be, we take this one and say it goes from 0, 1, 2, up to n minus 1, or any one of these levels. Then we take one of these, and this is minus L to 0 to plus L, whole number increments. And then the last one is the easy one, spin quantum. It can be plus 1/2, minus 1/2. Okay, each one of these, let's go on up to 3. Yeah, go up to 3. This one is given the letter S, this one's P, this one's D, and this one's F. Okay, so how many f orbitals have the value n equals 3? Well, if we say 3 here, then what are the possible ones here? 0, 1, and 2, right? You can't have f's at that level. So that's why the answer is 0. Okay, trick question. Okay, 26. How many f orbitals have n equals 6? Okay, if n equals 6, then we can do up to, we can get f's here. When we're talking about f orbitals, this is a shell, this is a subshell, this is an orbital. So we're talking about orbitals. If we say n equals 6, then we can have the f orbital here. And that means we can have 3 or -3, -2, -1, 0, +1, +2, +3. 1, 2, 3, 4, 5, 6, 7. Okay. And relate that to the periodic table. These are the elements with f orbital filling, and there are 14 of them. Right? 2 electrons, 7 orbitals, 14 possible elements. Excuse me. 27. If n equals 2, how many orbitals are possible? Okay, now if n equals 2, what can we have? We can have 0 and 1. So if n equals 2, then L can be 0 or 1. And the orbitals then, m sub L, can be 0 for this one, -1, 0, and +1 for that. So you can have 4 if n equals 2. 28. I got room to do one more here. A given set of p orbitals consists of how many orbitals? Well, here's the p's here, and we can have -1, 0, +1. So you can have 3. You can have 3 orbitals at the subshell p. Okay, and 29. Which of the following is an incorrect designation of an atomic orbital? All right, is 1s true? Let's see, A, B, C, D, and E. Right? 1s, 3d, 1s, 3d, 1p, 4f, 1p, 4f, and 6s. Okay? Any n can have an s. That one can have a 0. This one has a 0. This one has, they all have zeros. Right? So any of them can have an s. This is okay. This one's okay. 3d. Okay, if you have 3 here, you can have 0, 1, and 2. That one's good. 1p. If you have a 1 here, you can only have an s. Can't have a p. Right? And if you have a 4, you can have a 0, 1, 2, and 3 because that's n minus 1. So that one's good. So C is the one that's bad. You can't have a 1p. All right. Let's make some room. How are we doing on time? We've got till when? 1:45. Okay. $31. A point in the wave function where the amplitude is 0 defines what? What we're talking about here, the wave function of an electron in an atom. And that point where you have an amplitude of 0, where the amplitude of the wave means that you're not going to find an electron there. It just won't be there. And that's called a node. And that's a term that's used in just about every wave expression, whether it's sound or light or whatever. A node is considered wave amplitude of 0. Okay, how many electrons in an atom can have a quantum number N3L2? Okay, N equals 3, L equals 2. All right, we're down to this 2, right? We can't go any further than this one, so we're working here. We're saying how many electrons. All right, so if we went from this one to m sub L, this would be -2, -1, 0, +1, and +2 times 2 electrons. So it'd be 10. Right? 33. How many electrons can be described by the quantum numbers N3, L3, m sub L1? N3, L3, m sub L1. Well, let's see. N3 could have what? 0, 1, and 2. 0, 1, 2. You won't have any electrons, right? That's not possible. That's got to be 4 before L can be 3, N minus 1. Okay, trick question. Just see if you're paying attention. 34. What's the L quantum number for a 4s orbital? Well, 0, 1, 2, 3, S, P, D, F. If for a 4s, right, then the L quantum number is 0. That's what S means. S means L0. All right, 37. Let's see, which of the following combinations of quantum numbers does not represent permissible solutions of the Schrodinger equation for the electron in the hydrogen atom? Which combination of quantum numbers is not allowed? Okay. So if we had, let's do it this way. N, L, m sub L, and m sub S. And we have A, B, C, D, and E is all are allowed. So A is 9, 8 minus 4 and a half. 9, 8 minus 4 1 half. A, B, C, D. The next one is 8, 2, 2 and a half. 8, 8, 2, 2 and a half. And then 6 minus 5 minus 1. Minus 1 and a half. And then 6, 5 minus 5. 6, 5 minus 5 and a half. Okay. Is this one allowed? Yep. N minus 1. That one's allowed. And if this is 8, we could have -8 up to +8. So that one's covered. Right? And a half is fine. So A is okay. 8. Can we have a 2 out of 8? Well, yeah, we can go from 0, 1, 2, 3, 4, 5, 6, 7. How about this one? Right? -2, -1, 0, +1, +2. That one's good. Right? 6. Can't have negative numbers in L. It's got to go 0, 1, 2, 3, 4, 5. Right? That's your ringer right there. And this one should be fine. 6, N minus 1, -5 up to +5. That's good. That one's good. So C is your bad boy. 40. Who was the first chemist to recognize patterns in chemical properties of elements? The temptation is to go straight to Mendeleev. But patterns were recognized before Mendeleev. He just put everything together into a more coherent story. And he also said that this element, this space in the table is missing. One day you're going to find an element and this will be its characteristics. But before that, Dobereiner came up with his triads. Right? That was the first recognition of patterns. '41. Mendeleev is given most credit. Oh, I already told you that one. He emphasized the usefulness of the table in predicting the existence of properties of unknown elements. That's what gives Mendeleev the lion's share of credit for the periodic table. That was B. And we're going to 44 next. The complete electron configuration of 10 is. All right. So 10 has how many electrons? Well, if it's neutral, it will have 50. So this is we're going to string it out here. What you have to do here is go through the, in order of increasing energy. Right? So the simplest way to do that is use the periodic table. Right? Lowest energy is going to be 1s. Right? Got 2 electrons. Come down to the next period. Now we have 2s, lithium and beryllium. 2s, fill that up. Then we come across the boron, that's 2p. Right? These are all p filling orbitals. The first 2 columns are s filling. The middle transitions are d orbitals filling. Okay? So once you got that straight in your head, we can just move on across there. Down to 3, we're back to 3s. And then we come across to aluminum, that's 3p. Okay? You have to know how many electrons can go in each one also. Right? 2 in the s's, 6 in the p's because they're -1, 0, and +1 with 2 each. Okay? 3p. All right, we get across there, and then we go back to 4s for potassium and calcium. Then we get to the D's. We go scandium to copper. But we have to back down 1 n. So we're in the 4th period, but the orbital is 3d. Right? There are 10 elements across there, so 10 electrons. Then we come to gallium. And gallium, we go back up to 4p. And we go all the way across 4p to krypton. Then we go down to 5. 5s2. Now we go to 4d with yttrium and on across. So 4d10. And once we get over to cadmium, now we've got 2 more steps at 5p. That should be 50. So let's see. 2, 4, 10. 2, 4, 10. That's 20, 30, 40, and 2, 4, 6 is 10, 50. That's it. That's how you use the periodic table to fill in your electronic configuration. Because it's constructed very nicely that way. Then you don't have to use that that drawing I gave you. I mean, it's in the useful information if you want to use it, but I like this way better. That was 44. And that would be D. D would satisfy. 46. Oh, while we're here, how would we abbreviate this one? Well, you work your way back until you find the very next noble gas. So we work our way back 2 here, 10 there, 2 there, and up to krypton. Krypton is 36. And then what's left over from krypton is these guys right here. So you'd have krypton plus these would be how you would write the abbreviated version. All right, where was I? 46. Let me see. Yeah, I can make it. Make it over here. Probably at least make it to finish 52. That would be a good break point. If I run out of time, that's the best place to stop. Okay, 46. The statement that lowest energy configuration of an atom is the one having the maximum number of unpaired electrons allowed by the Pauli principle in a particular set of degenerate orbitals. So, okay. Did I use that term before, degenerate? I don't think I did. So when you have p orbitals, right, your p's, you've got three, actually the subshell p, you've got three subshells, -1, 0, and +1, right? D's, you have five, right? -2, -1, 0, +1, +2 for D's, right? Because this is, well, S is 0, so it only has one. This is 0, this is 1, this is 2. I'm not going to go to F's. These are known as degenerate orbitals. That doesn't mean that they're perverted. They have dirty minds. It just means that they have the same energy level. So these three are at the same energy level. These five are at the same energy level. And Hund's rule, which is the answer to this question, says that as you fill these degenerate orbitals up, you have to unpair them first. If you've only got three, that's great. If you got a fourth one, then you can start pairing them, or a fifth one, or a sixth one. But you can't pair them until you've got at least one in each degenerate orbital. That's Hund's rule. And that statement there is a convoluted way of saying that. All right, let's see, 47. An element has the electron configuration krypton. We just did that. That's 10, isn't it? Okay, so this is 10. So where is it located to answer that question? Non-metal, transition, metal, lanthanide, actinide. It's not a lanthanide or actinide. It's not down in here. It's up there. And 10 is actually a metal. Yeah, see, it's a metal. It's to the left of that jagged line. 48. An element with the electron configuration xenon 6f, 4f, 14, 5d7 would belong which class on the periodic table? All right, well, all we have to do here is you see that the S is full and the F is full, right? 14, 7 times 2 is 14. The one that's only partially filled is D7. So 5D7 would be in the sixth period, because once you move from 6S, you go to 5D. So 5D7 would be 1, 2, 3, 4, 5, 6, 7 be iridium. Right? And that's a transition element. Okay? Okay. Let's see, who's next? 49. All alkaline earths have the following number of valence electrons. Which column is alkaline earths? No idea. First one's alkaline metals. Second one is alkaline earths. They have 2 valence electrons in the s orbitals. Okay. At 50. 50 says titanium has blank in its d orbitals. Titanium is 22, and it goes from 4s2 to 3d2, correct? Yeah, 3d2. So it has 2 electrons in its d orbital. Okay, it's the second one over in the transitions: scandium, titanium. Scandium is 3d1, and titanium is 3d2. Uh, 52 is iron. So iron has how many? 26. Okay, what's the question? How many electrons? It's unpaired in its d orbitals. All right. So if we're only looking, we're looking at the transition. So there's 3d something. We would expect 3d, let's see, it's 4s2, and then 3d what? 1, 2, 3, 4, 5, 6 in iron. Like that. So with D's, you got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Yeah. So that's 1, 2, 3, 4 unpaired electrons. Okay. Based on Hund's rule. Let's see, we're going to do 53 and 54 from that table. Nitrogen has 5 valence electrons. So which represents the ground state for nitrogen? I'll get that one while I'm erasing the board. Um, 53. Nitrogen has 7. So there's so few, we can go ahead and write the whole thing out. 1s2, 2s2, 2p3, right? That's 7. Okay, so this one's going to be 3 degenerates. 1, 2, 3. These guys are going to have that. These guys are going to have that. 2, 4, 5, 6, 7. Which represents the ground state for nitrogen? It would be A. Right? They skipped 1s and just gave us the 2s2 and the 2p3. Okay. How about 54? Which represents the ground state for N minus? N minus still has 7 protons, but it has 8 electrons. So if we put that extra electron in here, it has to go there. Okay, and that's E. All right. We're coming on okay. $55. In which group do all the elements have the same number of valence electrons? All you have to do for these is to find them in the same group. Right. So A through E, A, B, C, D, and E. So the first set is phosphorus, sulfur, and chlorine. Well, phosphorus and sulfur, chlorine, they're in the same period, but they're not the same groups. None of them are. right? So they would not have the same number of valence electrons. Silver, cadmium, and argon. Well, argon's not related to either one of those other guys. So you only have to look at them. Sodium, calcium, barium. Sodium is an alkali metal. Calcium and barium are alkaline earths, right? So that was not going to work, right? Barium's way down here. Calcium and barium are fine, but sodium's in the wrong group. Has a different number of valence electrons. Phosphorus, arsenic, and selenium. Phosphorus and arsenic are fine, but selenium is shifted over one. Mendeleev could have told us that one. They don't bear a resemblance to one another. And we know from subsequent work that the valence electrons, the number of valence electrons, are different. Of course, Mendeleev didn't know that at the time. He just knew their relative weights and their physical and chemical properties. So E, none of them. None of them share the same number of valence electrons. All three of them in each group. 58. Of the following elements, which has occupied d orbitals in its ground state neutral atoms? Occupied d orbitals. So if it's got d orbitals occupied, now it doesn't say that they're the highest ones being filled. It just says, does it have them? Okay, that's the trick to that statement. So if you look at barium, yeah, barium's way down here. It's gone through 2 levels of Ds already. So barium, yeah, barium does have occupied d orbitals. How about the other guys? Calcium? Calcium hasn't got to the Ds yet, right? So it has no Ds. Silicon? Silicon has no Ds, right? It's 3 Ps. And phosphorus, right? Phosphorus is too high up, right? And chlorine is still too high up. So the only one that has d orbitals in it is that first one, barium, in its ground state. That's an important distinction. Because if you get excited, if you excite an atom, you can move electrons into the d orbitals if you put enough energy into them. All right, we're talking about ground state here, the lowest energy stable atoms. That's all we've done so far. Yeah, we made one ion, right? But we haven't promoted any electrons to higher energy levels. Let's see. 59. We didn't do 59 yet. So same group of elements. The following elements, which needs 3 electrons to complete its valence shell. All right. To complete its valence shell, we just say, all right, 3 electrons. We just go to the noble gases and back up 3 places. Right. So it'll be in the nitrogen group, nitrogen. Nitrogen, phosphorus, arsenic, antimony. Phosphorus is there, D. That takes 3 electrons to fill its valence shell. Makes him look like a noble gas. So. All right. 62. Let's see. Oh. I'm already past that point. Let me see. What would be a good place? Okay. I'll stop at 66. Which of the following atoms has 3 electrons in p orbitals in its valence shell? P orbitals are being filled in this group over here from boron, aluminum, gallium over. So you want to know the number of p orbital electrons? Just count from the left. 1, 2, 3. That's the nitrogens again. Okay. So out of that group that we have there, the only one that is in the nitrogen group is bismuth. Way down there at the bottom. Vanadium's a transition element. Gallium is the first one in the series. It only has one p orbital electron, and barium, in its outer shell, it doesn't have any. Well, barium's got all its p's filled anyway, so it has 6 electrons in its p orbital. The only one that has exactly 3 is bismuth. Let's see, one more, and then we can pause. Yeah, that's a good place to pause. 66. Then we'll talk about periodic trends when we get back on Thursday. Which of the following is the highest energy orbital for a silicon atom? That's kind of an incomplete statement. The highest energy orbital occupied by electrons, right? Because highest energy orbital could be, up to infinity, right? So what we should say is, which is the following is the highest energy orbital occupied by electrons in the silicon atom? If we take it to mean that, then we say, all right, where's silicon located? It's in the carbon group, and it has 3, period 3, 3s, 3p2. Yeah, 3p is the highest occupied orbital.